Next, we want to be able to do some simple things like manipulations of parametric equations now that we know what they are and how to graph them. So the first thing we want to learn how to do is we want to learn how to eliminate the parameter. All right, so eliminate the parameter means we want to get rid of it. We want to get rid of t. So let me say that. Or theta, or whatever particular variable we've got. So that means that we're going to write our curve as a y equals f of x, or an x equals a g of y, right, by solving one equation for t. We already did this once. I was playing with this when I was getting rid of the parameter on that linear one. And then we substitute into other equations, or the other equation, I should say. All right, so it's pretty straightforward. So if I look at this particular problem, I have an x, which is equal to 3t squared minus 4, and I have a y that's 2t. Well, all right, if I'm going to solve one of these for t, right, obviously the y is way easier to solve. So if y is equal to 2t, then y divided by 2 is equal to t. So I will take that and I will plug that into my x. X is equal to 3, and then I'll make it y divided by 2 squared minus 4. All right, so that would be x is equal to 3y squared over 4. So 3/4 y squared minus 4. And there you have it. So that's an equation. It's an equation in x. So what I'm doing is I'm making x of y is equal to 3/4 y squared minus 4. And because Desmos, of course, is so powerful, it can graph functions in y. Functions in y. Sorry, my 3 looks weird there. Oh, now my whiteout is weird. Come here. There we go. So Desmos will graph this for us. Let me show you. So the function itself is right here. So I was just playing with this. All right, so if I play here, so there's the parametric curve, like that, right? Oh, I'm going to make it go. If you want to play with the directions, it's currently going backwards and forwards. I'm going to make it just go forwards. There we have it. And I can slow it down or I can speed it up, etc. So I'm going to make it slow down just a little bit. All right, so we can see it's pulling this parabolic curve. And then if I look at the g of y function that we just built, there it is. 3y squared over 4 minus 4, right, divided by 4 minus 4. And that's the whole curve. It's a function in y. It passes the horizontal line test, but not the vertical line test. So if you wanted it as a function in x, well, then you'd have to struggle a little bit more. So we have to solve that equation for y. See what they're asking us to do? Solve that equation for y by hand. All right, well, let's see here. If I have x equals all this stuff, then x plus 4 is equal to 3/4 y squared minus 4. Oh, got rid of the minus 4, sorry. Then I wanted to multiply by 4/3 to both sides. Right, that'll make things easier. So that'll get me, let's see, 4/3 x plus 16/3 equals y squared. Oh, I was just sitting there thinking if they're both over 3, we could actually put them together. And then, of course, you need to take the square root of both sides to get y by itself because you're solving for y. So that would mean that 4x plus 16 over 3, I would take plus or minus the square root of that, and that would be y as a function of x. There's 2 of them there because, of course, it's not a function in x. That's why you need 2 pieces. It doesn't pass the vertical line test. So if I turn off this one and I turn on this one, this has the negative down here in the green, and then the positive, I just turned it off accidentally, right there in the blue. Right? Together, they make that function, right? And as y as a function of x. Right? It's a lot easier if you just let yourself have a function in y, but they specifically asked for both of them, so there we have it. Well, they asked for this one. This is the one they wanted. But if they don't ask for one in particular, then the other one would work fine. All right, so that's how to eliminate a parameter. It's not too bad. It involves substitution, which is an algebra trick we've known for a very long time. Now, what's really interesting is how do you go the other way? How do you introduce a parameter into a function? And the answer is there is no one single way to do that. I cannot stress this enough. There are infinitely many ways to do this, to parameterize a function. You're rewriting that function in parametric form. Now, a very good way to start, besides at the very beginning, that's a little Sound of Music shout out, is to let x be equal to t. If you let x be equal to t, then you can create the other function, right? The y function that'll go with it, and then it'll work out. I'll show you in a second. But I wanted you to realize there's not just one way to do this. There are infinitely many ways. And they relate to each other, and I'm going to show you that in this example. So we're going to come up with 3 separate sets of parametric equations. I might actually come up with 4, I don't know. 3 separate sets of parametric equations for y equals x cubed. For a -6, which is less than or equal to x, which is less than or equal to 6. Okay, so they're giving us a domain here. All right, so the easiest way to do this is to let x be equal to t. If x is equal to t, then y would be equal to t cubed. And then your domain for your parameter would be -6 is less than or equal to t, which is less than or equal to 6. There is one version. That is the simplest way to do this. Sorry, that was bugging me. Simplest way to parameterize y equals x cubed. Oh, but it's not the only way. Let's try another one, shall we? Let's let x be equal to 2t. Sure, why not? You can make it whatever you want. So if x is 2t, then y would be x cubed, which is 2t cubed, which is 8t cubed. All right, then what about our parameters? Our parameter was given us to us as -6 is less than or equal to x, which is less than or equal to 6. So that'd be -6 is less than or equal to 2t, which is less than or equal to 6. And if I divide everything by 2, I would get -3 is less than or equal to t, which is less than or equal to 3. So the next parameterization would be 2t. Let me just do it this way. X equals 2t, y equals 8t cubed, and -3 is less than or equal to t, which is less than or equal to 3. All right. Well, there's nothing special about 2t. I mean, I could do it with anything. 3t, 4t, 5t, pi t, e to the t, whatever. So if I let x be equal to 1/2 t, let's try that. Then y would be 1/2 t cubed, which is t cubed divided by 8. Now, how would that parameters change? Again, it's -6 is less than or equal to x, which is less than or equal to 6. So that's -6 is less than or equal to 1/2 t, which is less than or equal to 6. And that would mean if I multiply everything by 2, -12 is less than or equal to t, which is less than or equal to 12. So the next parameterization would be x equals 1/2 t, y equals t cubed over 8. For -12 is less than or equal to t, which is less than or equal to 12. And my challenge to you is that all 3 of these curves will sweep out y equals x cubed from -6 to 6. So how do they differ? Well, let's look at it in Desmos. And this is where Desmos really shines. This is that curve. You can see, if I turn off the parameterizations for just a second, that is that curve, y equals x cubed. No question about it. And it's from -6, which is less than or equal. Actually, I didn't even put that in. I can do that, though. I have to put it in here. Sorry. Oh, I went from -8. I'll go -6. Sorry. -6 is less than or equal to x, which is less than or equal to 6. Right there. And I'll let a go from -6 to 6. So we can see this. All right. So there's the curve. Isn't it beautiful? Now, the first parameterization we did is right here. And again, I'm not sure why I had these if I wanted 6, but that's so be it. All right, so if I sweep out that curve, you can see that point right there. It's sweeping through that curve, right? If I turn off the curve, you can still see it follow that path, right? All right, now what about 2t, the next one I did? And again, I actually accidentally have this going from way too far away. So that was -3 to 3 here. There we go. Amazing, isn't it? So it starts off in a different spot and it kind of sweeps in and sweeps through. Now, why is it going further? Well, that's because of what I have going on here with my A values, because A is starting at -6, but I can't change that for every problem. So I just want you to see. But notice the speed. Look how the green goes much faster than the blue. Now, if I put in the third one, which we did, which was t over 2, right there, it's that orange one. See how slow it's going compared to the other two? It sweeps through the curve, but boy, is it slow about doing it. And of course, I would have to change my A values to -12 and 12 in order to get them to show, right? So let me do that. Back here, right there, the orange one starts, right? Then you hit 6, then the blue one comes in, then you hit, right, 3, and then the next one comes in. Amazing, isn't it? Right, so that's the difference between the parameterizations. They're all going to follow that path, but they're going to follow it at different speeds because, of course, your parameter t is related to that, to time. So there are infinitely many. I actually made up another one, which is t cubed, if you wanted to see it right there. So if I graph it right there, you can see, oh, that's that curve. Right there it is. Right, that curve is going through. And that one goes even faster. If you look for the black dot, it's even quicker because t cubed is going through so fast. It's there and it's gone in a flash. Whereas the orange one is so slow. Right? But they all, 4 of them, follow that path. They follow that curve. So that's what I mean when I say there are infinitely many parameterizations. There's lots and lots of ways to do this. The easiest and simplest way is just to let x be t. Right? That's pretty straightforward. But all these other ones will work, and they might have different value. In other words, there might be reasons why you might want a fast one or a slow one, having to do with maybe the physics applications of the problem or something like that.